Hi, I'm Tyrone Keynes, and today we're going to be exploring the difference between linear and nonlinear functions. I've been using linear functions in the model we've been building over the last few weeks. That model would be the Keen Financial Instability Hypothesis model. What I do when I start getting complex in my model is I will build complex parts of that model separately. And that's what I've done here is I've built my nonlinear equations to see how they would react so I could adjust the constants and see the shape of the curve that I wanted for my model. One thing important to note is just because it's nonlinear doesn't necessarily mean it's going to add all these complex dynamics. What we're doing when we're adding a nonlinear equation is we're adding realism to our model. So with the linear equation, we could have employment go above 100%, and we want to figure out a way we can constrain that, and we can do that with nonlinear equations. So right now I'm going to show you the shape of a linear equation, and we'll use the wage change function in our model, and I'll just show you that right now. I'll set it at 60% employment. That means 60% of the population is employed. I'll press start and we'll run it, and as you can see, it's a straight line, and anything over 60% employment, wages will be going up. Anything below 60% employment and wages are going down. As you can see, it's dropped below 1 and we are at 49% employment. That's a simple equation. So right now, I just changed the slope. So let's just see what that looks like. So I had a slope of 11, so a steeper slope. And now I've changed it to 10 where I'm at the model, and that just makes it a shallower slope. So the slope is right there of 10, so S employment, and then the zero wage change is Z employment. So anything over 60% employment will mean wage growth. Very simple. But what I want to do is change this into a nonlinear function. And so I've created a switch, and we're going to put this switch in the model so we can see the difference between the nonlinear and linear effects. I'll switch it over to nonlinear. You can see right here in this little switch block, when you make a switch, this is a heavy side only switch. So at 0, and I'll switch it to 0, it'll be at the 0 input. And that'll take an input from our linear function. If I switch it to 1, it goes to the 1 input, and that takes an input from our nonlinear function. And then the output is our employment function. So I've switched it to the nonlinear function here. And we're just going to run that, and we're going to see the shape of the curve. I'll go to 61 will be good. A little different here because the shape is different. I have at 66% employment, there is a change. So 66 or 67 and up, there's a wage change. And we'll run it and just show you the shape. And I'll adjust it. And as you can see, we get a nonlinear shape here. Basically, it's a concaved curve, upward sloping. So basically what it's saying, as employment increases, wages increase exponentially, and this makes it an exponential function. The equations here are still quite simple. It looks complicated in the wiring. We can look at it in the actual mathematical expression here. So this is our linear function right here. So the employment linear function equals the slope of employment times employment minus the zero wage change of employment. And then the nonlinear equation here is slightly more complicated. We use an exponential operator, but really, if you're into math, this isn't a very complicated equation whatsoever. And when you're doing the wiring, if you're not familiar with math too much, this is actually an easier setup. You get a flow of your math. So this is x to lambda. X lambda means 66 or 67% of the population is employed. There'll be an increase in wages. This is the slope, a lot shallower than 10 because of the shape of it. If your min employment or min lambda was you can make it flatter. So let's run it here, and I'll show you. So we'll get our shape going. So that's our shape as we got it set up. Now I adjust and make this even more, and that basically flattens the curve. I'll go right down to 0. So you're losing the concave shape of it. And I'll go back to my original setting here, which is minus 40. Stop it, run it again. Get our shape going. If we go too quick, it won't solve it so well. But that's our shape. That's what we're creating. So at low rates of employment, there's not much wage change. Instead of it just precipitously dropping the whole way down, at lower rates of employment, okay, so wages aren't going to drop dramatically. But at really high rates of employment, they're going to really rise at a high rate. And we have the same thing going for our investment function. Slightly different parameter settings, but it's the same deal. Now, the government spending function is a downward sloping function. So here we had an upward sloping function, while the government function is downward sloping like that. And it's basically the opposite of employment. And it uses the same input, employment. So we'll run the model here. And we will adjust our employment. And as employment goes up, government spending goes down. As employment goes down, government spending goes up. And that's the function we've created here. And we're going to put that into the model. So we'll go to our model right here. We'll move this out of the way since I've had the luxury of setting up and adjusting my parameters. I can go right away into just copying and pasting what I need. We'll go like this. Lasso the variables that we want. Right click, copy selection. We'll go to our model that we finished off last week. We will paste our selection. We'll wire it together. We're going to need a copy of output, which we're using Y, or in the Greek letter Y, which is gamma. I'm going to copy that. Copy selection, paste selection. We will need that in a bit. We'll flip it. We're going to create an input. So we'll call this G underscore I is for government input. We're going to wire that into our equation. We're going to group this. Lasso all the variables you want grouped. Right click, click group. We've got a grouping. The group logo is facing the wrong way. Right click, and we will flip the group logo. If you right click again, you'll notice you can flip the contents as well, but our contents are facing the right way. We will resize our grouping to an appropriate size. We will zoom in to our group, and we will pull the government input variable to the back of the group. We'll do a little reorganization here. We'll unwire that. We'll use a time or multiply operator. Flip that. So from the function, we'll multiply it by the output. And let's add a spending switch. So we'll call this gov spending. Make that a parameter. We'll start its initial value of 0, and because this is a switch, its max in this situation will be 1, its min will be 0, its step size is 1. We'll grab a switch block, rotate the switch block. We will wire the government spending into the switch block. We'll create a unnamed constant, and it'll be 0, meaning there'll be no output if we have this switched off, meaning there's no government spending. We'll wire that into the first input or black input of the switch block. We will wire our function multiplied by output into the second input of the switch block, which is the red input tab. And then we will wire the output from the switch block into the government function. And then we will put the government function into the slot of the grouping. And now we have our group. Zoom back out. We will try to wire this together, so we'll need to wire from employment, and since employment is already sitting in another group, I'll just take it before from the operator to join into a group variable, so an input variable in another into a group. You have to zoom in right now. It's just a Minsky bug. So you have to zoom into the group so you can see the variables within the group. Then you can wire. Like so. Then you can zoom back out. Now we're going to create a stock called government spending. We'll integrate it. I believe we will want to flip this variable that way. And we'll call this G underscore S for government spending. G underscore S. We'll give a slight rotation. We'll try 40 degrees here. Wrong input box. Right here, 40 degrees. That looks pretty good. Wire out of the government function into the integrate block GS right there. And then we will wire that GS into the plus input of the subtraction operator that feeds into net profits. And we now have a government function. We can adjust our wiring to give a better flow effect. Like that. Same with this wire. Kind of like that. Wire here. Make it nice. Now another glitch in Minsky is if you start naming too many groupings, the program crashes. Just another reason why we need more funding for Minsky. So I will use a note and name this government spending function. That'll work. And what I'll do is I will add my nonlinear equation for wages, the wage function. I'll just simply copy and paste, and I'll also do that with the investment function. And then I'll come back and show you what I've done. All right, so I've added my nonlinear functions with the switch, so we can switch between the linear and nonlinear functions. We've done that also with our investment function, so linear and nonlinear functions have been added with the switch block. A few other changes I made. I put our control bar here along the side with our linear, nonlinear switches and our government spending. I've changed some of the graphs. One of the things is I've used a differential block, which is right here, so we can differentiate the change over time. So if you remember, integration is a measurement of everything, the change below the line, which is a lot more stable and what system dynamics programs use. But if we want to just measure the change in a number, the line, we can use a differential block. And I've been throwing all these, you can call them auxiliary variables, into this group down here to save room. And I've added this new one here. So output, differentiate it, divide it by output into a percent operator equals our output growth rate. So instead of just the constant growth in the waves, we're going to see a percentage of change, which is just a neat little feature, you could say. And that would be this graph here. I've changed the variable. I've added some bookmarks here for our flow chart. Just because this model is now starting to grow, so we're going to start using the bookmarking feature. To bookmark, you can do it one of two ways. You can use it in your note, create a note, and click bookmark, and in the short description, write what your bookmark is, and that'll show up in your bookmark menu. Or the way I do it is I find specifically where I want to be on the canvas, then I go up into bookmarks and I click bookmark this position, and I name the name of the bookmark. So I have one for the graphs as well. So these are my graphs. I've added those lines, those function lines that I was showing you earlier for employment, profit, and the government function. Like I said, I changed output, so now it's reading the change. So yeah, we'll give it a run and see what it looks like with the linear So this is what the model looked like essentially in our last episode. Pretty basic over time. Now, when I click on our nonlinear equations, it adds more realistic bounds. And as you can see, there's the function change right there. In employment, the function change in profit. So that's kind of, and you can adjust that nonlinear equation to meet your expectations of what the change in your, let's say, employment, the range, and same with investing. It gives you a lot more control, so you can calibrate your model to make it more realistic to the real world. And of course, that changes the shape of a lot of our plots here. What I can do is add government spending. And this is going to stabilize our economy here. As you can see, there's pretty wild oscillations. Now you can see the government function here. And like I was saying, it's a downward sloping function versus an upward sloping employment function and profit function. And that'll bring some stability eventually to our economy. And we'll just start it again with the nonlinear equations and government spending. And what you're going to see is a convergence to equilibrium, essentially. Now, you might be asking, well, why doesn't the government just simply spend, and spend? Well, there's a social perception that deficits are bad. So that becomes an issue with the idea of spending endlessly. We'll just go in, make sure our switch is working. It is on. And sometimes if you're not getting the results you want, like I'm not here, I'm going to change that. So there will be spending, more government spending. There we go. We'll just turn that off now. What I did is, even at a high rate of employment, there's still going to be government spending. I had it set so it was at 60% employment. There's no more government spending. And what I did is I went into the parameter settings and I set it in such a way that even if there's 80% employment, there would still be government spending. So there are limitations to this model, because one could simply say, well, let's just government spend. Now, what we haven't added and what we're going to be adding in the next episode is inflation. So there is the school of thought, post-Keynesian, MMT, where government spending is good, but it is constrained by the fact that there is a lack of resources at the end of that thought process, and that is very inflationary. And we're going to be adding that function next week so we can explore that dynamic. And we will also have a mechanism where interest rates are endogenous in our model. So, and they'll be based very much off the inflation rate. So we're going to be adding nominal terms next week, an inflation rate, so a price index, and market interest rates. So the system itself will come up with the interest rates. So yeah, I will see you next week. Thanks for joining in. Okay, bye-bye.